Working with UL, NFPA, and national code bodies, several manufacturers developed new test standards that address the unique properties of factory-built systems. The result of these efforts is an exhaustive testing regimen that exceeds site-built standards. All tests must be witnessed by third-party independent testing agencies to validate test data. Factory-built systems were first recognized as alternative methods of construction in the 1984 BOCA Uniform Mechanical Code. Today, factory-built systems are recognized in all nationally referenced codes. Let's look at the test requirements for factory-built systems. One of the first tests to be performed is a real grease fire. Factory-built components are assembled in a prescribed manner and lathered with lard. The fire department is alerted and standing by. Then the lard is ignited. The real test is to confirm that the design remains liquid tight and will not fail under real fire conditions. Next, the system is tested in a simulated fire, external to the duct as prescribed in ASTM E814, standard test method for through penetration fire stops, and ASTM E119, standard test methods for fire tests of building construction and material. In this test, the duct is lowered into a large furnace where it is exposed to temperatures nearing 2,000 degrees Fahrenheit for a prescribed amount of time. This system was exposed for 3 hours. At the end of the test, the duct is immediately removed from the test structure and subjected to a hose stream, just as it would be in a real fire. The duct, supports, and fire stops must maintain their integrity. The purpose of this test is to ensure that a fire, external to the duct, would not be allowed to pass through a fire-rated partition and compromise the barrier. Wrapped rectangular site-built ducts are tested to the same standard. Today, alternative systems must also be exposed to and pass an internal fire test, complying with the test criteria as established in UL 2221 and ASTM E2336. UL 2221 is used for factory-built systems. ASTM E2336, also referred to as AC101, is designed for site-built and wrapped systems. These tests establish products to be in compliance with the model codes and classified as zero clearance to combustibles. Let's examine the testing procedure, beginning with a test sample fabricated from carbon steel. Here you see a certified welder constructing a 12 by 36-inch rectangular test sample. This is equivalent to a 24-inch round duct, a size often seen in hospitals, nursing homes, convention centers, prisons, and other medium to large service kitchens where life and safety issues are paramount. The steel is 16 gauge as prescribed, and the test duct is fabricated in accordance with the 2006 International Mechanical Code and constructed to the same criteria as test samples used at independent testing laboratories. This dimensional duct is very common where adequate ceiling height is not provided. This shows the duct being prepared for testing, properly supported, and being wrapped by independent certified insulation installers. 2 layers of 2-inch insulation are being applied to comply with the manufacturer's installation instructions. Weld pins are installed through the insulation and into the duct to secure it and prevent sagging. This system meets the requirements of AC101, ASTM E2336. When properly installed and the joints are lapped, the outside dimension becomes 24 inches by 48 inches at the lap. A 24-inch round equivalent duct becomes 30 inches to 32 inches in diameter, depending on the manufacturer and the code requirements. Before testing, thermocouples are secured directly to the insulation using the same type pads used in factory-built system tests. The furnace is attached and fired at 500 degrees Fahrenheit until steady-state temperature is achieved on all thermocouples. This generally takes several hours. Upon reaching steady state, the temperature is rapidly increased to 2,000 degrees and held for 30 minutes, during which time all 17 thermocouples are monitored. Average temperature cannot exceed 250 degrees above ambient. Any single reading that exceeds 325 degrees above ambient constitutes failure. Steady state was reached in 3 hours and 47 minutes. The burner fire rate was then increased to obtain the 2,000 degree temperature requirement. 4 minutes into the high temperature portion of the test, at about 1,700 degrees, the rectangular duct began to collapse. Notice the insulation on top of the duct starting to sag, indicating duct collapse within the wrap. 8 minutes into the test, with 2 of 4 thermocouples measuring input temperatures above 2,000 degrees, collapsing of the duct becomes even more apparent, and fire from the furnace began to erupt to the outside of the duct through the void left by the collapse. Then the collapse increased along the horizontal length of the duct. 12 minutes into the test, we were not able to maintain 2,000 degrees on any thermocouple measuring input temperatures. Catastrophic failure was obvious. The vertical section of the duct began to lean, and for safety purposes, the test was terminated. Our attempt to attain data for an accurate ASTM E2336 UL2221 comparison failed. We were surprised at the severity of duct deformation in such a short time. While the insulation remained in position as installed, this severe deformation has the potential to compromise penetrations through a fire-rated partition.